All right, let's jump straight into this explainer. Today, we are breaking down a seriously fascinating new algorithmic approach to AI sequence analysis. It's called Ladderpath. It's based on a recent arXiv paper that is making some major waves in the AI news space right now, and honestly, for good reason. We are looking at what could be a fundamental shift in how we process text, literally moving away from heavy statistical memorization and focusing entirely on underlying structure.
Here is our roadmap for today. We're going to start by looking at the problem with transformers. Then we'll introduce the Ladderpath approach, put it head-to-head against BERT, talk about why this actually matters for developers, and finally, look at how you can integrate it into your own workflows.
So, Section 1, the problem with transformers, Goliath's weakness.
Now, the fundamental question we have to ask ourselves is this: what actually happens when transformers encounter unfamiliar data? I mean, we all know that transformer-based models get their sky-high accuracy by memorizing statistical regularities across massive corpora of text. They are basically just learning token co-occurrence probabilities. But what happens when you only have a few examples, those tricky few-shot constraints, or when the data fundamentally shifts away from what the model was trained on?
Well, as long as you stay in distribution, accuracy stays great, mostly thanks to that surface-level token memorization. But the absolute second you introduce out of distribution, or OOD data, the performance just collapses. You get distribution shift, vocabulary mismatch, and the heavy weight of parameter bloat dragging it down. Because these models rely so heavily on statistical memorization, if the vocabulary shifts even slightly, they just don't have a true structural understanding to fall back on.
Moving on to Section 2, introducing the Ladderpath approach. Think of this as the David of text modeling. To really demystify Ladderpath, we first have to understand its foundation, which is algorithmic information theory, or AIT. Now, AIT shifts our focus completely away from learning dense embeddings through gradient descent. Instead, it operates on this really elegant core principle, describing data through minimal generative programs. So it's not about tracking how often two words happen to sit next to each other in a billion-word dataset. It's about finding the fundamental, bare minimum rules required to generate the sequence you're looking at right now.
Okay, so how does Ladderpath actually pull this off? It's really a three-step process. Step 1, it traverses the sequence. Step 2, it identifies recurring nested patterns at multiple nesting levels. And Step 3, it constructs a topological representation of those repetitions. So, instead of just blindly reading a string of words, the algorithm is actually extracting the underlying blueprint. It's pulling out the architectural DNA of the sequence.
And from that topological map we just built, the researchers derived three totally unique distance measures. First, there's a normalized compression distance, or NCD. You can think of this kind of like checking how much smaller a file gets when you zip it, but adapted specifically to the Ladderpath topology. Then there are two alternative distance metrics computed directly from that hierarchical structure. And guys, what is genuinely revolutionary here is that these distances quantify similarity without a single parameter tuning loop. It literally just outputs a scalar distance mapping directly to structural overlap.
Let's hit Section 3, Ladderpath versus BERT, the head-to-head.
So the researchers took these three distance measures and integrated them with a simple k-nearest neighbor classifier. And when they benchmarked this across tasks, the results were just crystal clear. Under out-of-distribution and few-shot constraints, Ladderpath consistently takes the win. It drastically outperforms both gzip-based NCD and massive compute-heavy models like BERT in these incredibly challenging, low-resource settings.
You might be wondering, why does it win? Well, it's because it treats sequence structure as the primary signal. Structural compression preserves domain-agnostic patterns, which makes Ladderpath incredibly resilient to the kinds of syntactic variations and lexical shifts that normally just break embedding-based similarity searches. Traditional embedding models struggle the second domain boundaries shift because they're stuck on surface-level tokens. Ladderpath just looks right past those tokens straight to the structural hierarchy underneath.
Section 4, why this matters. Let's talk about the developer advantage.
There's a quote from the source paper that is an absolute game changer. It says, Ladderpath decouples sequence understanding from compute-heavy pre-training. Just think about the infrastructure overhead you're managing right now. With this approach, you no longer need to provision insanely expensive GPU clusters for fine-tuning. You don't need to constantly retrain models to adapt to new distributions, and you completely bypass the need to manage massive vector databases for high-dimensional embeddings.
Instead of dealing with opaque vector projections, you get a fixed, totally interpretable space where similarity is computed on demand.
And this opens up some really incredible practical applications. First, think about lightweight anomaly detection in logs or code where labeled data is super scarce. Second, you can do fast semantic clustering entirely without embedding model dependencies. And third, you get perfectly transparent similarity scores. Because every similarity decision traces back to specific nested repetition overlaps, it simplifies compliance and creates these amazing audit trails. It is absolutely perfect for streaming pipelines where labels just show up sporadically.
Finally, Section 5, integrating into your workflow. Here's a simple 3-step pipeline.
Now, the official GitHub repo hasn't been published by the authors just yet, but the paper actually gives us this really straightforward 3-step integration logic. Step 1, extract the Ladderpath structures. Step 2, compute the distance matrices. And Step 3, route those matrices to a k-nearest neighbor classifier. The source material even drops a minimal Python pattern using scikit-learn and NumPy. That means you can literally write the scaffolding right now and be totally ready to swap in the official distance algorithm the absolute second it drops.
So what should your immediate next steps be? Well, first, go clone archive paper 2607.5416 so you can verify the extraction algorithm and distance formulas for yourself. Next, plan to replicate that KNN integration on a held-out, out-of-distribution dataset just to validate the performance claims for your specific use case before pushing it to production. And finally, keep a close watch on the repository for code drops. Since hierarchical pattern matching requires traversing sequence structures, it's going to scale quite a bit differently than the matrix multiplications you see in transformers. So if you're running high-throughput production systems, you're definitely going to want to wait for optimized C++ or Rust backends to maintain those strict latency budgets.
As we wrap up this explainer, I want to leave you with a slightly provocative thought. Are we entering an era where structure actually matters more than statistics? With approaches like Ladderpath giving us lightweight, interpretable, and completely training-free alternatives, the way we model text and data might be going through a fundamental evolution right now. Definitely keep a close eye on these AIT-based approaches. They really might be the future of domain-agnostic sequence understanding. Thanks for hanging out with me today, and I hope this gave you a clear structural map of exactly where sequence analysis is heading.